Okay, so this is a section about now intrinsic viscosity. So we have talked about osmotic pressure for Mn and light scattering for weight average molecular weight. This time intrinsic viscosity and the Mark-Houwink equation, that's for the viscosity average molecular weight. And so that's where we are now for the stages. So today I'm going to talk to you more about the intrinsic viscosity. Intrinsic viscosity is the technique that has been developed and that it has been used for a long time and before the invention of other techniques. So it is a very kind of simple technique that is still can be used, and for this is a lot of theories are built upon the understanding the intrinsic viscosity, and by measuring this, you are able to estimate some types of average molecular weight, which is what people wants to characterize. And once again, I think you guys sick and tired of me saying the same thing. What is a concentration unit used in polymer chemistry? It is a mass per volume. Okay, so remember that we don't have a well-defined a single one molecular weight for the polymer. There is a distribution of polymer molecular weight. Sometimes it is actually hard to define what do you mean by mole. Okay, how many moles of polymer chains do you have, and they might not be the good representation about the situation. And okay, so let me talk about the intrinsic viscosity now. Intrinsic viscosity, we are using the symbol eta with a square bracket. Okay, so eta with a square bracket is an intrinsic viscosity, and it has a very different meaning than when people just say the viscosity. Okay, and the viscosity has a, for example, I think I mentioned this, the unit for the viscosity that can be measured by viscometer is typical centipoise or millipascal second. That's what you see. Whereas this one is essentially milliliter over gram. That's the unit. Okay, so it already has a different understanding. It is related to somewhat viscosity in the polymer solution, but it represents different meaning than the viscosity itself. So let's try to get on it. The viscosity measurement is using this various types of viscometer, and this is typically what they call for example here is this is the overload viscometer, that you are essentially putting your solution here, and then in the beginning you have a solution probably coming up this far, and then you're going to use a vacuum suction curve, the bulb, to really bring the liquid up to the level. And then what you do now is you see this little line here and the line up there, and so while this one is moving through the what is called a capillary, so what is important here is this is a section what is called capillaries. So the fixed volume, right? Let's say this is a fixed volume delta V is flow through the capillary shown up here, and we are going to measure the time for the solution and for the solvent, and we're going to assume that the density of those two are about the same, so that essentially that's what we are going to study. So what let's say what's the important part here is I'm going to blow it up, the area. So this is what it looks like. And then I just say, this is just a schematic diagrams, okay? So that's the most important actions are. And then you will see that if you look at closely, this one is actually has a thicker wall. So it's a capillaries. And then kind of they make a little notch there, a little notch there. So what you need to do is blowing up things here, move your liquid up, and then using the stopwatch, essentially how long does it take this fixed amount of solvent that I shaded here that is flowing through these little capillaries, right? So they have to go through this fixed volume. So that's a blown up version that you see up there. Okay. So where do I can find out this information? And so now even more simplified. So this is you can think about this as a one. Okay, this is a flow through the pipe, right? And with a diameter, well, radius of r, and then there is a pressure drops, which is a delta P. So it is a pressure drop, the pressure differences. So because of the pressure differences, there is a flow, and this pressure differences you can think of as the rho GH, as you learn, and this is what they call the Poisson equation, and the volumetric flow rate, dV dt. Okay, how much the volume through the pipe, right? So this is the volumetric flow rate. It will be proportional to the pressure drop, actually is normalized by the length, right? So this is in a way the length of the tube, and then there's a factor that goes in, which is a geometrical pi r to the fourth 8 times eta. Okay, that's a viscosity. So as you can see that the higher the viscosity is, the smaller the volumetric flow rate, and then we are going to see that this is the pressure-driven flow, and so I'm going to substitute that value with a rho GH. Right? And then what you are going to see now is I am going to rearrange this viscosity, right? This viscosity here is going to be because proportional, and this delta V is fixed, and I want to measure how much. What is my delta T, which is what I call here is a T, because T minus T naught, and T naught is a 0, right? So I just call the T, and then this is a rho GH, and the density is about the same density of the solvent, and we are dealing with a dilute solution, density of a solution, and I'm going to say they are about the same, and then later we're going to say the solution is about the same, but let's just at the moment it is a density times time for this one to flow through this capillary tube, and then there is a constant what I call K. So this is a very simplified relationship, because everything else, such as lengths, geometries, fixed volume, these are all like fixed parameters, right? These are all what is shown in the green box is all simple parameters. These are all fixed values. So I can say that if the actual viscosity, this viscosity is actually same as the viscosity shown up, and by measuring the time, how long does it take for this one to flow through this fixed amount of volume, fixed through it, and if you let me know the density, and there's a characteristic constant for each capillaries, and then you guys can solve, we can solve this. But what makes it this one even more friendly for somebody who doesn't really understand, who doesn't really do not want to go through the complicated math is the following. There is a different viscosity in the polymer solution chemistry that are using it. They call the relative viscosity. So they call the relative viscosity means viscosity of a solution divided by viscosity of a solvent. And we are using the notation for viscosity of the solvent as there are so many notations, so let me just leave it out like this. That's a eta naught. Okay. And then this is just say eta. Okay. And then what do I do is there will be the viscosity ratio. That's what we call the relative viscosity. Remember, this one has a no unit. That's interesting to notice here. And then to make it easier for you to do is, okay, although this means a viscosity ratio for the relative, and which is I think what we actually people are measuring this, and then if you plug in this equation through this equation shown in the box, and you will see that K rho naught T naught K rho T, and this is 0, and then we assume that this is not so much different, so they are about the same. That's because the density is about the same. Then it comes down to simple T over T naught. That's your relative viscosity. So all that is for you to take is just measure the time to flow, fix the volume through the capillary, that's the T, and measure the time for solvent and time for solution, right? And you just have to have the ratio, and you get the relative viscosity. Once you got the relative viscosity, you are in business, okay? So that's number one. And then the number two is a specific viscosity. It's nothing but what is an excess amount of the viscosity increase on top of what's already possible. So what that means is essentially it's nothing but relative viscosity minus 1. You can think about kind of the viscosity is I write it the same way. This is the same equation, but this is the viscosity of your solution divided by 1. But you want to essentially minus 1 means, physically speaking, you just want to subtract viscosity of a solvent from the solution viscosity. So that's the meaning of this. So specific viscosity is an excess amount, the viscosity increase intrinsic to the polymer solution. And the third one is they are going to say intrinsic viscosity is, okay, intrinsic viscosity is specific viscosity, but I want to divide by concentration, because the higher the concentration, the polymer will be have a higher specific viscosity. So this is a sort of the normalization of concentration contribution. And if you do in the limit of concentration goes to 0, that's what we define as intrinsic viscosity. So it's a series of experiments. You plot specific viscosity. This is a much common. The other one is less common. So specific viscosity divided by concentration at different concentrations shown up, and you plot. You prepare 5 solutions. All you gotta do is do this. Measure the time. How long does it take to flow compared to the time that is shown up there, and then you can do this experiment. So these are the 3 different viscosities, and as you can see that the specific viscosity depends on polymer concentration, and polymer chemistry community decide, okay, let's divide this one by C. That's sort of the linear regime concentration effect on specific viscosity. And what if I put this concentration goes to 0 in the limit of infinite dilution? That will give me the intrinsic viscosity. And this is probably one of the most well-studied quantities in the disciplines of polymer solution characterization, because that's the only doesn't use nothing much complicated, but simple capillary viscometer that is easily accessible. So this section that actually, how do you measure that? And this is, I'm just going to focus on this. So just once again, I'm emphasizing here, all you need is you measure the solvent time, and then you measure the solution time at different concentration. Right? So, and then you can have a ratio. So here's a homework assignment saying that, okay, cyclohexane, it takes about a little bit over 2 minutes, and then they prepare 4 different concentration. They give you a time, and then one little column that you guys can think about is, okay, I can make relative viscosity, and I can make specific viscosity, which is relative viscosity -1, and then I can essentially get the specific viscosity value divided by this concentration value to have specific viscosity divided by concentration, which has a unit of inverse concentration. Okay, and so then you do this experiment for throwing this liquid, essentially going all the way to the top, but your clock starts from T0 and you stop and T is T. Okay, so you do that experiment, you put this data into the plot here, and then I don't know, I'm just throwing the values here. For example, if you have a value looks like this, and then you're going to do the extrapolation in the linear, and that's the value. So which is, I would say, for example, this one is, I'm not saying this is an answer, I'm just giving you that's a 25 in my linear exploitation, and therefore my intrinsic viscosity is 25 milliliter per gram, right? Because once again, this is in the limit, concentration goes to 0, specific viscosity divided by C is what defines the intrinsic viscosity. Okay, and this intrinsic viscosity later on, I'm going to talk about K times A to M to the A. That's a Mark-Houwink equation, which is still being used in many polymer systems, because this is very important. And then they find out that the molecular weight for the polydispersed system actually becomes viscosity average later on. My final closing comment on this measurement part, I would like to emphasize the role of the immersing this one into the water bath. Okay, this is essentially constant temperature water bath. That's what this experiment is all about. Is actually, if you look at that, it's almost like a, in a way, fish tank. Okay. Literally, actually, I remember using the fish tank when I measured my intrinsic viscosity during my graduate school studies, and then you immerse this and make sure that temperature is constant and well equivalent in the steady state. So everything is the same temperature, and even you put your solutions here, right, before ready to go. And once you put your solution, I think that you want to make sure that you want to put the solution about here. So make sure that you want to put your solutions inside of here. And then, because let's say if this is a 30 degrees C, if your solution is 25 degrees C, you need to wait. You need to wait to make sure that you have given this solution is you want to be, this one is not 25 degrees C, gradually to the 30 degrees C. So, once you're loading your sample, make sure that you wait until everything is temperature is constant, because temperature is a big factor to do that experiment. And so this is actually one of my technicians, quite easy to do. All they need is a stopwatch, and they just put arrays of capillary viscometer immersed in a water bath, or something like a convection oven, like with a glass window, so that they can make sure that everything is very well equivalated, and so on. And particularly, this one is still in use if you are having a difficulty find some what I call exotic solvent. For example, what about something what if your solvent is sulfuric acid? I cannot really imagine myself doing the experiment, doing sulfuric acid, doing osmotic pressure experiment, or light scattering experiment. They'll be pretty tricky, okay? But still, I can do the intrinsic viscometer experiment as well. And sulfuric acid is probably, next time we're going to talk about the gel permeation chromatography. This is sulfuric acid using GPC. I don't know. I don't think it's people have that kind of harsh environment GPC instrument. So this is much more your last resort for people just to have an idea about the viscosity level that you guys have. Okay. Okay. Thank you. So this is the first section.